Okay, hi everyone. My name is Manuel Anglada-Tort and I'm a postdoc researcher in the Computational Auditory Perception Group at Max Planck Institute for Empirical Aesthetics. Today we'll be presenting a joint work with Peter Harrison and Nori Jacobi, where we use singing to study human cognition and cultural evolution. Like speech, singing is a form of vocal communication that requires the coordinated use of the vocal system. It's very clear here in this little video. And singing exists in every known human culture, and it has been mainly transmitted orally through generations. For this reason, singing provides a very interesting modality to study the biological and cultural foundations of human cognition and music evolution. Perhaps one of the most fascinating aspects of human song is that it exhibits a vast diversity of forms cross-culturally. And I have just a few examples for you today from this science paper by Sam, which is here. I just met him just before the talk. But at the same time, certain musical features are widespread and found in most musical traditions across the world. For example, large-scale corpus studies have found that melodies cross-culturally tend to use a small set of intervals or pitch categories per octave. Melodic intervals tend to be small in size. And melodies tend to use arced or descending musical contours, which is the sequence of ups and downs in pitch, shown here by the blue arrow. In this study, we're interested in how and why common and diverse musical features emerge from oral transmission. To study this, we developed an automatic online pipeline to perform cultural evolution experiments in the singing modality. This paradigm is inspired by a lot of previous work on iterated learning, both in language and music. In our method, participants are initially presented with a sequence of random notes and asked to imitate them by singing. We then extract the fundamental frequencies in their singing, and we generate on the fly a new input melody for the next participant. Over generations, participants' errors are amplified, and we can measure how transmission biases shape the evolution of hundreds of melodies. This is an example of how this looks from the participant point of view.
Da, da, da. Da, da, da.
So let's move into the results. I will start by presenting the results of one experiment with very short melodies. Here, participants sang to 3-note melodies. And we examined more than 300 transmission chains in a total of 57 US participants. Importantly, we use a cross-participant chain design. So basically, each transmission chain here is composed from different participants. Here, you can see the distribution of the intervals in the initial set of random melodies. So the way that this works is that we can represent all 3-tone melodies in this 2-dimensional space, where each dimension, the horizontal and vertical axis, represent one interval of the melody. So dots in this plot correspond to melodies, and yellow areas correspond to high density areas. This is the distribution of sung melodies in the first generation of the experiment, and this is the distribution in the last 3 generations of the experiment. As you can see, there is more structure over generations with few locations where there is more concentration here in the last melodies of the experiment. In fact, the entropy of the distribution of intervals decreases significantly over time, showing again that intervals increasingly become more concentrated in few locations. This is also clear again from this distribution. And what is interesting is that some of these popular locations in this space correspond to common interval combinations in Western music. So for example, in the top right corner, we have melodies that are around a major chord. And I have an example.
Ta, ta, ta.
And another popular area is this bottom right corner that correspond to melodies that play an arc-shaped contour. So these are melodies that go up and then come down to the same note where they started.
Ta, ta, ta.
So I will now move to the second experiment, which is exactly the same, but this time we use longer melodies composed of 5 notes or 4 intervals. And here we examine 120 across participant chains in 38 US participants. This time, because each melody has 4 intervals, I'm plotting everything in the same distribution. So here, I'm plotting the 4 intervals of each of the melodies in this space. And now what you are seeing here is the distribution of the initial random set of melodies. And here is the distribution of the first 3 generations of the experiment, and finally the distribution of the last 3 generations of the experiment. And again, what we can see is that over generations, melodies are becoming more peaky and more structured, and this is also confirmed again by the entropy of the interval distribution, which decreases significantly over time. Yeah, so using a peak finding algorithm, something else that we can look at is that the most prominent peaks in this distribution fall around integer locations and integer intervals. And this is interesting because we sample melodies randomly from the space. So we did not assume any discrete intervals a priori. I'm not sure if this is well seen, but we have integer locations here at 5, at 2, at -5, that fall quite well in these integer semitones. And something else that we can look here in the terrain of longer melodies is whether melodies end up with a unison in respect to the first note. So we know that in Western music, this is quite of a common feature, that melodies tend to finish with the same note that they start with. And in this plot, what I'm showing is the distribution of the interval between the last and the first note in our melodies. And as you can see, in the last generations of the experiment, melodies tend to finish with unison, so with interval 0, so it's the same note in which they started. So the next thing that we look at is what melodic structural features emerge from our evolving melodies. First, we find that melodies are biased toward a small set of intervals. And this is shown in this plot, where I'm showing the number of significant peaks found in the distribution of intervals over time. As you can see, the number of peaks decreases significantly in the two experiments. Second, we find that melodic intervals become significantly smaller over time. And what I'm showing here is in the vertical axis is the absolute mean interval size of the melodies in each generation, which you can see that is also decreasing in the two experiments. Third, we find that orally transmitted melodies increasingly exhibit arc-shaped musical contours. This is shown in this plot where each note in the 5-note melodies is averaged across all melodies in each generation. So as you can see, at the beginning, in the baseline, the musical contours tend to be more flat, and as well in the first generations of the experiment. But in the last generations of the experiment, melodies have this arc-shaped musical contour. And here I have an example.
Ta, 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 ta.
Okay, so far we've seen that certain melodic features emerge artificially from our evolving melodies. And these features are consistent with widespread melodic features observed in most musical traditions across the world. In the last part of this talk, I will present some very preliminary data, explorative data, that focus more on this question on how and why such melodic features might emerge. To address this question, we need to look at the complex interplay of transmission biases involved in oral transmission, such as motor constraints, cognitive biases, or previous cultural exposure. So in the experiments I presented so far, it is impossible to know to what extent the observed effects are because production constraints or perceptual constraints. This is a hard problem to tackle, but one way to explore this is by running perceptual-only experiments. So this is what we did here, where we ran a large-scale listening experiment where 400 US participants were presented with random melodic intervals and asked to rate how pleasant these intervals were. We tested a total of 14,000 unique intervals randomly paired with different pitches within a pitch range. These are the results. These are the aggregated results of the rating experiment, where the vertical axis indicates how pleasant the intervals are. And there are a couple of interesting things here. So again, what we are seeing is that despite the fact that we sample melodies randomly and continuously from the space, we again see that peaks tend to fall around integer semitones, integer intervals. And something else that is interesting is that some of the peaks that we are seeing here correspond to consonant intervals in Western music, such as the octave, the perfect fourth, perfect fifth at locations 12, 7, 5. And at the same time, in contrast, prominent dips correspond to dissonant intervals, such as the tritone at 6, -6, or the semitone at 1, -1. So using this data, what we can do then is to look at how much our singing intervals align with this empirical melodic consonance profile. And here what we find is that sung melodies from our experiments do increasingly kind of align with this empirical rating experiment. And what I'm showing here is the vertical axis in this plot shows how pleasant the sung intervals in our experiments are based on the empirical data from the rating experiment, and we are seeing this increase over generations. This suggests that perception and not only production influences the oral transmission of music. Another important transmission bias in singing involves the role of memory. To explore this, we ran an iterated singing experiment where the number of notes per melody was allowed to change from generation to generation. We started the experiment with the same number of melodies in different length conditions. You can see, so at the beginning of the experiment, we have melodies ranging from 4 notes to 12 notes. And what we are seeing is that over generations, there is this strong memory effect shaping the number of notes per melody with more chains converging around 5 to 6 notes per melody. I'm going to skip this for the time, and I'm going to move to the last thing I want to show you. So this last finding concerns a deeper issue regarding cultural transmission experiments, and this is what is the role of social transmission and individual differences in such experiments. To study this, we ran 2 experiments that are identical to each other, but only differ in their design, within or across. In the across-participant design, like the designs I've been showing you so far, melodies are transmitted between different participants, allowing for social transmission. In contrast, in the within participants design, melodies are transmitted individually within the same participant. And here I ran 2 new experiments. These are slightly larger in size, with almost 400 chains per experiment and about 125 US participants in each experiment. What we find is that in the cross-chain condition, the results replicate quite nicely the results that I showed you so far in the 3-note melodies, where melodies in the last generations are concentrated around very few locations. However, in the within-chain experiment, I get quite different results. In particular, the distribution of melodies is less structured and has way more peaks in different locations. Overall, this emphasizes the role of individual differences which are preserved in the within participants condition. In contrast, there is less variability in the across participant conditions, where social transmission seems to create stronger attractors in few locations. In fact, the entropy of the interval and pitch distributions confirm this result, showing that melodies become more structured in the across-chain condition than in the within-chain condition. And again, this suggests that social transmission plays an important role in the emergence of melodic structures, whereas individual learning alone does not seem to converge to the same results. To conclude, we introduced a novel method to perform large-scale cultural transmission experiments in the singing modality. And our method, we find that our method works efficiently in computers available to most people online. And this is very exciting because it reduces experimental costs while massively increasing the reach, scalability, and diversity of data collection. And of course, there are important limitations in this work, such as separating production from perception or relying only on Western participants. But I'm quite excited to address such limitations in future work, for example, by running cross-cultural experiments or perceptual-only experiments with sliders. I'm also excited to try similar paradigms with other production modalities, such as speech or gesture. Yeah, and I think that's pretty much everything. I would like to thank Norris Jacobi and Peter Harrison and all the members of the Computational Auditory Perception Group. And I'm looking forward to your questions. And yeah, thank you very much for listening.